Welcome to lesson number 9, en route flight. Now, air navigation is the art of directing an aircraft along a desired course and determining its position at any time. Now, you can navigate by pilotage using visible landmarks to maintain your course by dead reckoning. This includes determining your position based on heading, time, and speed, and by using navigational aids such as VOR or GPS. This lesson focuses on pilotage and dead reckoning skills. Now, lesson number 10 covers navigation with electronic aids. To plan a cross-country flight, you must understand basic navigation tools and skills used by aviators, which is in your flight planning bag of tricks, so to speak. Now, these skills include reading charts, choosing a route, using a plotter, and calculating time, distance, and fuel with a flight computer. You also need to know about classes of airspace and what's required to enter each type of airspace and how to distinguish types of airspace on sectional charts. After you finish planning a flight, you need to know how to execute that plan en route. This lesson is organized as follows: coordinate system, aviation time, topography, airspace, special use airspace, dead reckoning, turbulence, and power failure. Let's now join Josh Prusek in the classroom and get started.
To understand navigation, you need to know how to read aeronautical charts. The chart most often used for VFR flying and navigation by pilotage is called a sectional chart. Now, pilotage is using visible landmarks to maintain a desired course, and it's the basic form of navigation for beginning pilots operating under VFR. To understand the sectional chart, we'll begin with a discussion of latitude and longitude. Map makers use a grid of lines called latitude and longitude, illustrated here. The equator is an imaginary line equidistant between the North and South poles running around the entire Earth. The lines that run parallel to the equator are called lines of latitude. Now, they mark degrees of latitude north and south of the equator, and they range from 0 degrees north at the equator to 90 degrees north at the North Pole and 90 degrees south latitude at the South Pole. The lines of longitude or meridians run perpendicular to the equator and converge at the poles. The yellow line represents a meridian. Lines of longitude are designated from the prime meridian, or 0 degrees longitude, that runs through Greenwich, England, up to 180 degrees east and 180 degrees west. Here's how coordinates are marked on a sectional chart. Here is the 116-degree line of longitude labeled with a number. Each degree of longitude is divided into 60 minutes. Each minute is further divided into 60 seconds, and you'll find a tick mark halfway between each minute of longitude at 30 seconds. There's also a major tick mark at each 10 minutes and a minor tick mark at each 2 minutes. You have to look closely to see them. Lines of latitude are marked exactly the same way. In this example, you can see the 48-degree line of latitude. We know it's the 48-degree north line because we are north of the equator. Now, lines of latitude are divided just like lines of longitude. Below the 48-degree line of latitude is a line marking 47 degrees and 30 minutes. Now, just like longitude lines, each degree of latitude is divided into 60 minutes, and major lines mark every 30 seconds of latitude. There's also a major tick mark at each 10 minutes of latitude and a minor tick mark at every 2 minutes.
Okay, let's take some time now for an FAA test question on latitude and longitude. We want you to find the approximate latitude and longitude of Shoshone County Airport. There are 3 possible answers, but in order to do that, we're going to have to use a chart to help you out. So we go to our chart, find Shoshone Airport. There it is. Zero in a little bit tighter. There we have it. Now, the closest longitude, 116 degrees there, west. And if we come around to the center up on Shoshone, we see it's 116 degrees 11 minutes west. Our closest latitude is 48 degrees north. If we center it up, we have 48 degrees, 32 minutes north. And that's the correct answer there for our question is B. Now, that's pretty simple, but you've got to have the charts. You've got to be able to work with the charts to find that answer. Okay, let's get back to a new topic. This one, aviation time, with Josh.
Because airplanes often pass through several time zones during a flight, aviation uses a standard time system all over the world. It's called Coordinated Universal Time, and it's abbreviated as UTC. It's also referred to as Zulu time or sometimes Greenwich Mean Time. Now, UTC is the local time at the 0-degree line of longitude which passes through Greenwich, England. We use local time in our everyday ground-based activities. The lines of longitude or meridians that we just discussed are used as basic markers to divide the world into time zones. That's an approximate division because state boundaries and other considerations such as geographic features are also used to define time zones. You usually don't want a time zone cutting right through a town or a small island. Time zones are established at about each 15 degrees of longitude, which is approximately how far the sun moves across the sky each hour. So each time zone marks 1 hour. Now, the continental U.S. is divided into 4 time zones: Eastern, Central, Mountain, and Pacific time. If you travel from the West Coast to the East Coast, you add 3 hours to your trip because you cross 3 time zones. If it's 12 o'clock p.m. Pacific time, then you depart on that trip. Your departure time is 3 o'clock p.m. Eastern time. The time zones are shown here. Pacific Standard Time covers the Pacific states along the West Coast, as well as Nevada. Now, Mountain Standard Time covers most of the mountain states and the Colorado Rockies. Central Standard Time covers the Midwest from Texas all the way up to the Dakotas, and Eastern Standard Time covers most of the eastern United States and also extends up into Michigan. Now, daylight savings time is another thing to keep in mind. When daylight savings time is in effect, each time zone jumps an hour ahead of standard time. One more concept we need to review is the 24-hour clock. This is what a 24-hour clock looks like. Our day is divided into 24 hours, so instead of using AM and PM, the clock is divided into 24 segments as well. This is how you tell time using a 24-hour clock. First of all, midnight is 0000 hours. Now, 1 o'clock a.m. is 100 hours, 2 o'clock a.m. is 200 hours, and 6 o'clock a.m. is 600 hours, and so on until you get to 12 o'clock noon. Now, in the afternoon, just keep adding hours. So, 1 o'clock p.m. is 1,300 hours, 2 o'clock p.m. is 1,400 hours, 3 o'clock p.m. is 1,500 hours, and so on. Coordinated Universal Time is always expressed using the 24-hour clock. And as you'll see, using this system makes calculating and using times for flight plans and weather reports much easier. Now, how do you determine Coordinated Universal Time? Suppose you're in the Pacific Standard Time Zone and you want to convert to UTC or Zulu time. Well, just add 8 hours to the local time. So, 10 o'clock a.m. Pacific Standard Time is 1,800 hours Zulu time. Now, when daylight savings time is in effect in the Pacific Time Zone, add 7 hours to get Zulu time. Here's another example. If you're in the Mountain Time Zone during Standard Time, simply add 7 hours to get to UTC or Zulu time. Now, when daylight savings time is in effect, you add 6 hours. Now, during Standard Time in the Central Time Zone, you would add 6 hours, and when daylight savings time is in effect, you would add 5 hours. Finally, in the Eastern Time Zone, just add 5 hours to Standard Time. During daylight savings time in the Eastern Time Zone, add 4 hours to get Coordinated Universal Time or Zulu. Note that as we speed up UTC time, you can clearly see the relationship between UTC and the various time zones.
Now, Barry, do you have a rule of thumb for accounting for time differences when flying between time zones?
Oh, how I wish I did. I think crossing numerous time zones is the curse and bane of the pilot. When I used to fly around the world, once a month, once around the world, it was the best airline duty I ever had. It was an 11-day trip, but after about 5 days, you'd wind up in Bombay, India, where the clock was about 12 hours off of home time. And there was absolutely no way to compensate for time zone changes. I'm one of the worst victims of that syndrome, the time zone syndrome. I found that in India I would go to bed hungry and sit down at the dinner table and fall asleep. I mean, there was just no way to synchronize my body with time zones when you cross them that rapidly. Even when you go from LA to New York or cross 1 or 2 time zones, it takes a certain amount of time to become adjusted. And the biggest secret about crossing time zones is that there is no secret. There is no way to compensate. You simply have to get to your destination and grin and bear the time zone change until you readapt. And in case you're wondering, it takes about 1 day for every hour of time zone change to adapt to a new time zone. For example, if you're going from LA to London, it's an 8-hour time zone change. I find it takes a week before you're fully acclimated to the new time zone. It's very, very difficult. Some people have less difficulty than others.
All right, let's take this test question on aviation time. You're at an airport in the Mountain Standard Time Zone at 16:15 Mountain Standard Time, and you depart for a 2-hour, 15-minute flight to an airport located in the Pacific Standard Time Zone. The estimated time of arrival at the destination airport should be A, B, or C. Now, in order to arrive at the correct answer, we're going to have to follow these steps. You departed at 16:15 Mountain Standard Time. Add 7 hours from Mountain Standard Time to get 23:15 for Universal Coordinated Time. You're going to travel 2 hours 15 minutes, and this is the time en route. That means you arrive at 1:30 Universal Coordinated Time. Subtract 8 hours for Pacific Standard Time, and this puts your time at 17:30 Pacific Standard Time. So, if we go back to our question, the answer is B, 17:30 Pacific Standard Time. That's the correct answer. Okay, switching gears a little bit here, let's talk about en route flight. Now, with as much experience as you have, do you flight plan based on pilotage, dead reckoning, nav aids, or kind of a combination of all?
Well, I guess it depends on the weather conditions and where I'm going and the mission at hand. But my favorite kind of navigation, frankly, is to connect the endpoints of my flight with a yardstick. I'm going from A to B, and I draw a long line. I like to go direct, I like to go straight. But then what I do is I modify that line with A, are there any obstacles or obstructions in the way? Are there any reasons why I shouldn't fly that direct path? And also, of course, you have to check NOTAMs and make sure there are no temporary flight restrictions or other kinds of restricted airspace that would inhibit you or prevent you from going direct. But if there's nothing in the way, I love to go direct. I like to take off on a heading and do what Lindbergh did. Shut everything off, fly a compass heading, and see how close I can get to my destination without turning on a single radio. I mean, I think anybody can fly from A to B these days using GPS, and dead reckoning navigation are becoming lost arts, which is why I love to continue to practice both. I think it's terribly important that pilots remain familiar with their navigational charts, sectional charts. I love to fly along and pinpoint my position using my fingers on the chart and keeping track of exactly where I am. Not only do you remain proficient at that kind of very basic navigation in case the electrical system fails and you can't use GPS, but it also provides a great deal of satisfaction that you can fly the basic way. I suppose if one can say if man were intended to navigate, he would do it with his eyes, and I prefer doing it that way. I love to fly topographically.
All right, let's join Josh in the classroom again for a new topic, topography.
VFR pilots typically use 3 types of aeronautical charts: the sectional aeronautical chart, the terminal area chart, and the world aeronautical chart. Now, all 3 charts include information about and symbols for airports, airways, obstacles, special use airspace, and other aeronautical data. The scale of the sectional chart is 1 to 500,000, which means that 1 inch equals 6.86 nautical miles. Now, sectional charts are designed for visual navigation of typical light aircraft in VFR conditions. They show terrain relief and useful checkpoints such as towns, roads, railroads, and other distinctive landmarks. Sectionals show the most detail for a general area, and they are revised every 6 months. Now, a terminal area chart looks a lot like a sectional chart, but the scale on this chart is 1 to 250,000, which means that 1 inch equals 3.43 nautical miles. Now, these charts are for a specific city with Class B airspace, and in other words, they show more detail than a sectional chart, but they cover a much smaller area. The World Aeronautical Chart has a scale of 1 to 1 million, which is more convenient in faster aircraft that travel long distances. It depicts cities, railroads, distinctive landmarks, and so forth. Now, these charts have less information about airports and airspace than a sectional chart, and they are revised no more than once a year. Now, let's take a detailed look at a sectional chart, starting with the legend. It shows how airports and other information are depicted on the chart. Now, you can answer many questions on the FAA knowledge exam and the oral examination portion of the practical test just by referring to the legend. For example, this section of the legend shows that airports with control towers are shown in blue and all other airports are shown in magenta. The legend also shows information about other types of landing facilities, such as private airports, heliports, and even seaplane bases. Here's a guide in the legend that explains the details associated with an airport control tower frequency, lighting, and so on and so forth. Now, this part of the legend shows you the symbols used for VORs and other navigational aids. And here's a detailed breakdown of the details associated with radio navigation aids, like VORs and information about how to contact a flight service station. Other parts of the legend describe how airspace and obstructions are shown on the sectional chart. You can find descriptions of the symbols that alert you to unusual activities, such as glider flying and even skydiving here. And here's information about topographical features, like roads, lakes, buildings, and so on and so forth. Now, familiarize yourself with the legends on the chart. They provide to you during the FAA knowledge exam a wealth of information. Remember, you can answer many questions just by referring to the symbols and other information in the legend. Now, this is Shoshone County Airport, and it's identified by a magenta circle with a line that shows orientation of the runway. Shoshone County Airport also has an information box which provides details about that particular airport. The first number is 2223. It's the elevation of the airport, which is 2,223 feet above sea level. Now, the L that we see indicates that this airport has lighting, or lights for nighttime operation. The number 55 is the length in hundreds of feet of the longest hard surface runway available at Shoshone County Airport. The last 2 digits are dropped, so 55 indicates that the runway is actually 5,500 feet long. Now, some airports have a unicom frequency or a multicom frequency, and in this case, it's 122.8. The magenta circle with a C indicates that 122.8 is also the common traffic advisory frequency for this airport. Now, let's take a look at Garrison Airport. The magenta circle tells you that Garrison is an uncontrolled airport. Now, you would use frequency 122.9 indicated by the C in the magenta box to make traffic reports at Garrison. You'll also learn more about the CTAF and Unicom in Lesson 5. This chart shows Sulphur Springs Airport, and Sulphur Springs is located just southwest of a navigational aid. This box in the center shows a VOR DME. VORs and VOR DMEs always have a compass rose encircling the nav aid, and the compass rose is aligned with magnetic north. Around the compass rose, tick marks, arrows, and numbers designate the radials that beam out from the VOR. Now, here is the 330-degree radial from the VOR, and this is the 180-degree radial from the VOR here. You'll learn how to use navigational aids in Lesson 10, but for now, let's go into more details about how they're shown on the aeronautical charts. Now, the legend describes the symbols for navigational aids, and the first symbol is a hexagon with a dot inside, and this depicts a VOR. The next symbol is a VORTAC. A VORTAC combines a VOR and a military navigation system called a TACAN. Now, the third symbol is for a VOR DME. It combines a VOR and distance measuring equipment. Now, the magenta symbol marks a non-directional beacon, or sometimes referred to as an NDB. While rare, areas such as Faranagot National Wildlife Refuge are shown with blue dots bordered by a solid blue line like we see right here. Now, you should maintain an altitude of at least 2,000 feet above the highest obstruction in these areas. Now, this flag is a visual checkpoint when used when flying in or around Class B, C, or D airspace. The name of the checkpoint in this case, Springfield, is underlined and printed in bold type. Now, visual checkpoints are associated with buildings and other prominent landmarks such as small towns. When possible, always fly near these checkpoints and use them to report your position to a control tower or an approach control when you want to enter their airspace. Air traffic controllers also may use these checkpoints and ask you to fly towards them and report when you reach them. Now let's take a look at obstructions like this radio tower and how they are shown on a sectional chart. This triangle symbol marks an obstruction, probably a radio tower. Now the height of the tower is shown in text next to the symbol. Heights are shown with two numbers, one in bold, the other in parentheses. The bold number in this case, 400, is the height of the obstruction in mean sea level altitude. 295 is the height of the obstruction above ground level. So in other words, this tower is 295 feet tall, which would be 400 feet MSL as read on your altimeter. If you were flying anywhere near this tower, you would want to be well above 400 feet MSL. Now, here's another obstruction symbol. This larger symbol has lines radiating from the top. You can see it right here, and these lines show a lighted obstruction. This is obviously helpful information when you're flying at night. Again, note that the top of the tower is 1,086 feet above ground level, or 1,181 feet MSL. And while now only available in Alaska, a T in a blue circle near a navigational aid indicates a tweeb or a transcribed weather broadcast. Now you can hear the tweeb by tuning in the frequency for that particular nav aid. In this case, a tweeb is broadcast on an NDB on the frequency of 365 kilohertz. Now, elevation is obviously very important to pilots, so let's talk about how it's shown on these sectional charts. These color-coded boxes are a key to the color coding of the terrain. Low elevations are shown in green, and as elevation increases, the color changes to pale yellow, then into brown, orange, and then finally red. Now, contour lines are often drawn at 500-foot intervals. Near Garrison County Airport, you can see shades of green and tan separated by contour lines. Now, the colors illustrate different elevations in the area. You can compare the elevation of the contour lines to the height of the obstructions. For example, this obstruction is marked as 2,212 feet above sea level and 262 feet above ground level. That information makes sense when you compare it to a nearby contour line, which marks the elevation as 200 feet MSL.
All right, time for a question on topography, an FAA test question. What is the minimum altitude that's required to fly over the Cedar Hill TV towers in the congested area south of NAS Dallas? The minimum altitude. Now we've got A, B, or C, but in order to find that answer, we're going to have to go to the charts to help you out. Here we are. We've got the blow up of Cedar Hill TV tower, and we can see that the obstruction is 2449 MSL, or 1640 AGL. Now, if we go back to our question, the correct answer would be 3449 feet MSL. You get there by this explanation. The height of the tower is the 2449 MSL we saw on the chart. A 1,000-foot clearance is required between obstructions and aircraft over a congested area. So you take the 2449 plus the 1,000-foot clearance equals the 3449 MSL that we arrived at. Got it? Okay. Moving on to a new topic. The next one up with Josh in the classroom, airspace.
Now let's discuss airspace. There are several classifications of airspace with different operating requirements. We'll discuss the classifications of airspace, equipment requirements, pilot qualifications, and special use airspace, and how each type of airspace is shown on a VFR sectional chart. Note that the weather minimums, ceiling, visibility, and cloud clearance for operating in each type of airspace are also discussed in Lesson 4, Regulations. Once again, here is the legend typically found on a sectional chart, terminal area chart, or world aeronautical chart. Now, the area in the legend depicts airspace boundary designations. Here's a close-up of that legend. Note the airspace classifications are based on shading color and line type. Note that the column is split for clarity only. Here's an overview of the 6 airspace classifications we'll cover in this lesson. Class A, Class B, Class C, Class D, Class E airspace, and Class G, starting with the least restrictive, Class G, and working our way all the way up to Class A, which is the most restrictive airspace. F airspace is not used in the United States, so we won't discuss that here. Let's begin with the least restrictive airspace, Class G airspace. Now, Class G airspace is also known as uncontrolled airspace, and it's the least restrictive type of airspace. In the early days of aviation, there really wasn't much traffic and not many airplanes flew around in the clouds. So most airspace in the United States was called uncontrolled. Let's take a look at a sectional chart to see how Class G airspace is designated. In fact, Class G airspace isn't really specially marked on the charts at all. It's the airspace outside the boundaries of other airspace. It's uncontrolled airspace. For example, this is Oman Airport, and it's located in a sparsely populated area in the mountains as indicated by the brown and orange elevation contours. As you can see, it's also a private airstrip, but there are no lines or shaded areas around this airport, so it lies in Class G airspace. Now, you can think of Class G airspace as standing for government-free. Air traffic control may provide VFR traffic advisories in Class G airspace if controllers can see you on radar and they can communicate with you. But in Class G airspace, pilots are responsible for avoiding one another, and that's tough because the minimum weather required for day VFR flight in Class G airspace is just 1 mile visibility and maintaining clear of clouds when you're at 1,200 feet or less above the ground. Now, IFR flight is allowed in Class G airspace, but the pilot must be instrument rated and the aircraft must be IFR equipped. Now, to operate in Class G airspace, you must also have at least a student pilot certificate. ATC services are available for VFR traffic advisories on a workload permitting basis. Now, there are no special aircraft equipment requirements to fly in Class G airspace. By definition, you also do not need clearance from ATC to operate in Class G airspace. The next type of airspace is Class E controlled airspace, and it's controlled airspace as you can see right here. You can think of the E in Class E as meaning for everywhere else. There are more stringent weather minimums in Class E airspace, and because there's a good bet that except when some remote areas are near a city, if you're flying above 1,200 feet AGL, you're in Class E airspace. Class E airspace is used primarily to separate IFR and VFR aircraft on low-altitude Victor airways and around airports when the weather doesn't meet basic VFR minimums. Now, here's a Victor airway used to navigate between navigational aids. You can see the blue line marks the airway right here in the center line. The shaded lines represent the boundaries of the airspace and the Class E airspace, which extends for 4 miles on each side of the center line. This makes the airway 8 nautical miles wide. Now, Class E airspace on Victor Airways begins at 1,200 feet AGL and extends up to, but not including 18,000 feet MSL. It is designated as controlled airspace. Let's take a look at a 3D depiction of a Victor airway. As we've seen, an airway is 8 nautical miles wide. It starts at 1,200 feet AGL and it goes all the way up to, but not including, 18,000 feet MSL. You also find Class E airspace in a transition area as shown by this shaded magenta circle here at Imperial Airport. Now, Class E transition areas typically surround airports that have instrument approaches but no control tower. Class E transition areas protect IFR traffic as it approaches, and departs an airport. Now, the ceiling of Class E airspace normally extends up to 1,200 feet AGL. Class E transition areas begin at 700 feet AGL, and you must have basic VFR weather minimums to enter a Class E transition area. Now, Class E airspace also comes in another variety called the Class E surface-based area, as shown by the dashed magenta line here at Rollins Airport. This airspace surrounds airports with precision approach paths. Class E surface areas are designated at airports that have an automated weather observation system or a certified weather observer. Surface-based Class E airspace typically encircles an airport, and it may even have an extension that gives it a keyhole shape like you see right here. The extensions protect the approach paths that IFR traffic will use. Now, VFR pilots must have at least VFR minimums to enter this airspace. Here's a 3D view of surface-based Class E airspace and a transition area. The transition area starts at 700 feet AGL and it goes all the way up to 1,200 feet AGL. The Class E surface area starts at the ground and joins the transition area at 700 feet. Now, you can see that this airspace resembles an upside-down wedding cake. Here are the minimum qualifications and services that the pilot must possess in order to operate in Class E surface area. For pilots flying under instrument flight rules, ATC provides separation between other IFR and VFR traffic in the area. It also provides us VFR traffic advisories on request when workload permits. Many students wonder why you don't have to talk to a controller in Class E airspace. That's an excellent question. Class E is controlled airspace, but in this case, controlled really means basic VFR weather required. As we've seen, Class E airspace is designed to keep VFR traffic away from aircraft operating under IFR, when low clouds and poor visibility limit everyone's ability to see and avoid other traffic. If the weather meets basic VFR minimums, you can fly in Class E airspace without talking to ATC. Now, what are the equipment requirements for Class E airspace? Well, there is no special equipment required to fly in Class E airspace under VFR, so even the most basic airplane can fly in Class E airspace provided the weather meets the basic VFR criteria. And you do not need a clearance from ATC to operate in Class E airspace in good weather.
Okay, the discussion's airspace. Let's take an FAA question to test your knowledge. Unless otherwise specified, Federal Airways include that Class E airspace extending upward from which of these? A, B, or C? Now, from your lesson in the classroom, you'll be able to recognize this graphic. We're going to show you some of the dimensional information. 8 nautical miles wide, 1,200 feet AGL, and up to, but not including, 18,000 MSL. So if we go back to our question, the correct answer is B. Federal Airways are part of Class B, C, D, or E airspace. They are 8 miles wide, 4 miles either side of centerline. They are usually at 1,200 feet AGL and continue up, but not including 18,000 feet MSL. So B, your correct answer. All right, let's join Josh back in the classroom for further discussion.
Now we'll discuss Class D airspace. Now, Class D airspace is established around airports that have control towers. Here's the Class D airspace around McNary Field in Salem, Oregon. It's marked with a dashed blue line. You can see it right here. Check this 3D graphic of Class D airspace. Now, it's controlled airspace, and an easy way to remember Class D airspace is to think D for dialogue. It's established around tower-controlled airports. You must establish two-way communication with the control tower before you can enter Class D airspace, regardless of the weather. Now, Class D airspace is usually a cylinder that begins at ground level at an airport and extends to approximately 2,500 feet AGL. Now, the top of each Class D airspace area is shown on the sectional chart. You'll see it right here. And it's indicated by a 2-digit number in a blue box. Here you can see that the ceiling of Class D airspace at McNary Field is 2,700 feet MSL. Ceilings and floors of airspace are listed in hundreds of feet with the last two digits removed, so this 27 means the ceiling is actually 2,700 feet MSL. The field elevation at McNary is 200 feet above sea level, so adding that to the 2,500 feet AGL for standard Class D airspace gives the top at 2,700 feet MSL. Class D airspace typically has a radius of 4 nautical miles and it's centered on the airport. Some Class D airspace includes extensions and cutouts, so make sure that you note the dashed blue lines on your chart. Here's a 3D picture that shows Class D airspace embedded within Class E airspace. Many control towers don't stay open 24 hours a day.
Welcome back to the studio. Let's take another FAA test question on airspace. This one, a blue segmented circle on a sectional chart depicts which class of airspace? A, B, or C here. The letters A, B, or C. Of course, you recognize this from what you just saw in the classroom. And that segmented circle is recognizable as Class D airspace. Correct answer, C. We can see that the Class D airspace is shown with that blue segmented circle right around the edge. Okay, now let's go to Josh back in the classroom for some additional discussion of airspace.
So if a control tower is closed and weather reports are not available, the Class D airspace around the airport usually reverts to surface-based Class E airspace marked with a dashed magenta line. Now, if the tower is closed and no weather information is available, the Class D airspace then becomes Class G airspace. So check the airport facility directory for specific information on tower operating hours and Class E airspace effective times. Now, there are some restrictions when operating in Class D airspace. For example, you need to obey a 200 knot speed limit when operating at or below 2,500 feet AGL and within 4 nautical miles of the primary airport within Class D airspace. If you want to fly an ultralight aircraft in Class D airspace, you also must get permission from ATC prior to flight. And you also can't do aerobatics in Class D airspace unless you get prior approval from ATC. Some Class D airports are surrounded by a terminal radar service area, also known as a TERSA. Now, a TERSA is shown on a sectional chart as a dark gray circle and numbers that indicate the top and bottom of the TERSA airspace. An approach control provides VFR radar traffic advisories to you in a TERSA. Now, you aren't required to talk to approach control, but it's always a good idea. Now, here's what a TERSA looks like. It's typically established at airports that are busier than a typical Class D airport. You'll also find TERSAs around some military airports. Now, you must have a communications radio and a transponder to receive ATC services in a TERSA. Now, the minimum pilot qualification for operating in Class D airspace is a student pilot certificate. Now, before you can fly solo in Class D airspace as a student pilot, your instructor must provide ground and flight training on Class D operations and endorse your logbook. Now, ATC services available to you in a Class D airspace include VFR traffic advisories. But remember that as the pilot in command, it's always your responsibility to look outside and make sure that you see and avoid traffic. Remember, Class D means dialogue. That means you need an operable two-way radio prior to entering Class D airspace, and you must establish communication with the control tower. However, a clearance is not required to operate VFR in Class D airspace.
Back for another FAA test question on airspace. This one. Airspace at an airport with a part-time control tower is classified as Class D airspace only. A, B, or C? Now, from your classroom discussions, you recall these graphics. Class D airspace surrounded by Class E airspace. When the tower is not operating and weather information is not available, it reverts to Class E airspace. So the correct answer here would be C, when the associated control tower is in operation. Class D airspace means a control tower is in operation. If the tower closes, it reverts to Class E airspace. Back to Josh in the classroom for further discussion.
Now, Class C airspace is a little more complicated than Class D airspace. Class C airspace is centered on medium-sized airports with airline traffic such as Milwaukee, Wisconsin, Tucson, Arizona, and as shown here in Portland, Oregon. You'll also find Class C airspace surrounding military airports. There are a large number of aircraft, including airliners. Now, all traffic operating inside Class C airspace must establish communications with air traffic control and receive radar services. Now, Class C airspace has similar dimensions from airport to airport. Class C airspace is marked with solid magenta concentric circles, often shown with some cutouts around nearby airports. Now, Class C airspace is also typically divided into sectors like pieces of pie. The ceiling and floor of Class C airspace are indicated in hundreds of feet, as shown here at Portland. These numbers, like a fraction, show the top and bottom of the airspace in a particular segment. Remember, the numbers shown on the chart indicate hundreds of feet MSL, so in this case, the floor of the Class C airspace is at 2,300 feet in this area right here, and the top is at 4,000 feet. Now, the inner ring of Class C airspace begins at the surface, as shown right here, and extends all the way up to 4,000 feet AGL. Portland is close to sea level, so airport elevation plus 4,000 feet for the ceiling gives us a top of 4,000 feet MSL. Now, the base of the Class C airspace in the outer area typically starts at 1,200 feet AGL. Remember, though, that Class C airspace is tailored to fit each individual area. So always note the charted altitudes and boundaries of Class C airspace around a particular airport. For example, the Portland Class C airspace has a floor at 2,300 feet MSL in this part of the outer ring to allow for airplanes to fly above hills and still remain below 1,200 feet AGL. Now, here's a 3D view of Class C airspace. Think of the C as communications within 20 nautical miles of the airport. Remember, radar services are mandatory in Class C airspace, so you must have a transponder. Now, as you approach Class C airspace, first establish two-way radio communication, and second, watch out for traffic. A typical Class C airspace has an inner core from the surface with a radius of 5 nautical miles. The outer area typically has a radius of 10 nautical miles from the airport. Now, Class C airports also have a 20 nautical mile outer area. Radio contact is not required when operating outside the Class C airspace, but it's a good idea to call approach control when you're in the outer area and let them know your intentions because there's a lot of traffic around the Class C airport. Now, the upper layer usually starts at 1,200 feet above the surface, and the ceiling is usually at 4,000 feet AGL. Remember, however, that the numbers on the chart show altitude in MSL, which is what you read off your altimeter in the cockpit. All aircraft must have an altitude reporting or Mode C transponder to operate in Class C airspace. As you probably know, a transponder sends a code to the ATC radar screen. The Mode C part of the transponder signal transmits your altitude from the encoding altimeter in the cockpit. Now, all pilots must establish two-way radio communication with ATC before entering the airspace. That's why you want to start thinking about communication with ATC when you're about 20 miles out. Class C airspace has a speed limit. You may not exceed 200 knots indicated airspeed while operating below 2,500 feet and within 4 nautical miles of the primary airport. You may also not perform aerobatics or fly an ultralight aircraft in Class C airspace. Now, ATC communication is established when ATC replies with your call sign or your N number. This is important because if ATC says stand by or does not use your call sign or N number, you can't enter Class C airspace. However, you do not need a clearance to fly in Class C airspace. Now, the minimum pilot qualifications for operation in a Class C airspace is a student pilot certificate. However, before you can operate solo in Class C airspace as a student pilot, your instructor must provide ground and flight training on Class C airspace operations and make an endorsement in your logbook. Now, ATC services available in Class C airspace include IFR-IFR separation and IFR-VFR separation. IFR aircraft are always separated from other IFR and VFR aircraft. But remember, when the weather is VFR, all pilots are still responsible for avoiding other traffic, even when they're receiving VFR advisories from ATC. Now, equipment requirements in Class C airspace are an operable two-way radio to establish communications, and remember, you must have radio contact with the aircraft's N number.
What do you see as the biggest opportunity for a VFR pilot to ensure safe passage between departure and arrival?
Well, when operating in high-density airspace, and I presume that's what you're really talking about, there's not a lot one can do except try to choose routes that are out of the way of arrival and departing IFR aircraft, if those routes are known. And they're usually published, at least in the high-density areas, on the back of charts. They're called flyways. Avoid the flyways. But when you start talking about avoiding traffic and preventing mid-air collisions, the single biggest thing I can think of today is to avoid burying your head in the cockpit and studying these glass cockpits, spending too much time with GPS systems and so forth. I know that all this new high-tech stuff is a lot of fun, and there's a lot of advantage to it, but I have seen so many pilots spending so much time with their heads in the cockpit, not looking out the window.
Welcome back. Let's pick up another FAA test question for you on airspace. This one, the maximum indicated airspeed at which aircraft may be flown when at or below 2,500 feet AGL and within 4 nautical miles of the primary airport of a Class C airspace is which of these? Now, from your discussions in the classroom, we'll show you some graphics. This looks pretty familiar here, I'm sure. Speed restricted to 200 knots below 2,500 feet and within 4 nautical miles of the primary airport. So, for Class C airspace, what's the correct answer? It's A. You'll see that the speed was restricted to 200 knots below 2,500 feet and within 4 nautical miles. Okay, let's take another question. What is the normal radius of the outer area of Class C airspace? Is it A, B, or C? Now, this is the outer area. We'll have to take a look at some graphics here to help you with this answer. We've got the surface, we have the core, the radius, and the outer area radius. And from this, we can determine that C is the correct answer, 20 nautical miles for the outer area radius. Okay, we have yet one more FAA question in this section. This one is, what is the minimum radio equipment required for operation within Class C airspace? The minimum radio equipment required. Have a look. Okay, from your discussions in the classroom, we hope you get this one. The correct answer is C. You need to have two-way radio communications and a transponder with mode C. But the question didn't say anything about mode C. It said a 4096 code transponder. What that really means is if the transponder has the capability of broadcasting with mode C, 4096 different codes, 4,096 different codes. Wow, that was a tough one. Hope you got it. All right, let's return to Josh with more information on airspace.
Now, Class B airspace is the next category of airspace we'll look at. On a sectional chart, Class B airspace is shown by these solid blue lines. Class B airspace is designed to protect the main arrival and departure paths for airliners and to protect the airports that they serve. So the shape of Class B airspace does vary from airport to airport. Now, Class B airspace has another unique feature called the Mode C veil, which you see right here. The Mode C veil is a ring that extends 30 nautical miles from the primary airport at the center of the Class B airspace. The Mode C veil is marked by a solid magenta line and labels. Now, you must have a transponder with altitude reporting capability to fly within this ring, even when you remain below or above the Class B airspace, and even if you're not required to communicate with air traffic control. Class B airspace is established around the country's major airports. It serves a large number of airplanes, and you can expect to find air carrier operations. There's also mandatory radar service for all traffic. It generally serves more than one airport as well. Again, here is a typical Class B airspace around Seattle. The Seattle-Tacoma International Airport lies in the center. Now, by definition, Class B airspace surrounds big cities, and it's hard to see all the detail you need on a sectional chart. So the FAA publishes terminal area charts for all Class B airspace. Now, here's a 3D view of a typical Class B airspace. It has layers like an upside-down wedding cake. The primary airport in Class B airspace is located in the center at the bottom of the ring. You can see that right down here. The airspace starts at the surface and then often tops out at 10,000 feet MSL. But remember that each Class B area is unique, and many Class B areas have ceilings below or above 10,000 feet MSL. So check the chart for each Class B area that you fly in to make sure you know the upper limit for that airspace. The radius of the top layer of the Class B airspace is typically around 20 nautical miles. Now, each layer below has a smaller radius. Remember, you need a specific clearance to fly anywhere inside the stacks of Class B airspace. Note the magenta circle, as we've already pointed out, marks the 30 nautical mile radius of the Mode C veil. You must have an operating Mode C transponder to fly in this area, even if you remain outside of the Class B airspace. Now, because of the high volume of traffic around Class B airspace, ATC always needs to see you and know your altitude. Let's look at those ceilings and floors of Class B airspace in a little more detail. Now, each layer is marked on the chart with blue numbers, like you can see right here. They look like fractions. The top number always shows the top of the Class B airspace in that particular segment in hundreds of feet MSL. Now, the bottom number shows the bottom of that particular area. This label shows that the Class B airspace in the area starts at 3,000 feet MSL and ends up at 10,000 feet MSL. Now, all traffic must receive a clearance to operate inside Class B airspace. Establishing communications with ATC is not enough. You must hear the magic words, "Cleared to enter Class B airspace." Now, don't be afraid to ask the controller to confirm that you are, in fact, cleared into Class B airspace. You must advise ATC of your intended route and receive a clearance before you take off from an airport that lies inside Class B airspace. Note that ATC will often assign specific altitudes and headings for you to fly when you're in Class B airspace. You must comply with those instructions. Now, Class B airspace takes up a lot of space, so many Class B areas also have terminal routes to help low-altitude VFR traffic move efficiently around, under, and even in some cases, right through the airspace in VFR weather. One type of Class B transition route is called a VFR flyway. Now, VFR flyways are depicted on the back of terminal area charts, and as shown here by the white lines, VFR flyways are paths that take you under and around Class B airspace. Now, you don't need a clearance to fly along a VFR flyway because you're outside the Class B airspace. Although communication with ATC isn't required when you're following a VFR flyway, it's always a good idea. You must also have an operating transponder with an altitude reporting capability because you are inside the 30 nautical mile Mode C veil. Now, many VFR flyways also have preferred altitudes based on the direction that you're flying or your proximity to the airport that you're operating near. You should use these altitudes whenever weather and terrain allow. Now, another type of VFR route associated with Class B airspace is a VFR corridor. Now, a VFR corridor is like a tunnel that goes right through the center of Class B airspace. It allows pilots to transition Class B airspace without receiving a clearance and to enter the Class B airspace provided that the weather is at least VFR. Now, you must have an appropriate Class B chart to fly in a VFR corridor, and you must comply with all charted altitude, speed, and other restrictions while in that VFR corridor. VFR corridors have specific lateral and vertical limits, and you must make sure that you stay within those boundaries and use the appropriate ground checkpoints when you're operating in the VFR corridor. Some VFR corridors also include specific radio frequencies for contacting ATC or making position reports. Now, what are the Class B airspace restrictions? First of all, you must have a private pilot certificate or a student pilot certificate with a proper instructor endorsement to fly in Class B airspace. Your instructor will provide the logbook endorsement after you've received training on how to operate within a specific Class B area and at a specific airport in that Class B airspace. However, some of the busiest primary airports in Class B airspace are simply off limits to all student pilots. Now, ATC separates all aircraft in Class B airspace. Here are the equipment requirements. First of all, you must have a radio to communicate with ATC and a transponder with altitude reporting capability to fly in Class B airspace. And you cannot enter Class B airspace until you receive a specific clearance from ATC.
Welcome back to the studio once again. Let's take a couple of FAA test questions. This one having to do with radio equipment as well. What minimum radio equipment is required for VFR operation within Class B airspace? Remember now, this is Class B. Is it A, B, or C? One correct answer. You got your answer? Okay. What minimum radio equipment requirement for VFR operation in Class B airspace? The answer is B. Two-way radio communications equipment, a 4096 code transponder, and an encoding altimeter. All right, let's take one more question before returning to the classroom. This one. What is the minimum pilot certification requirement for operation with Class B airspace? Minimum pilot certification requirement for Class B airspace. A, B, or C? Have your answer? Okay, let's reveal it. The minimum requirement is B, a private pilot certificate or a student pilot certificate with appropriate logbook endorsements. All right, let's get back into the classroom with Josh as he continues on airspace.
Now, operations in Class A airspace are conducted under IFR and a clearance is required. Therefore, no VFR flight is allowed. So, therefore, there's no VFR minimums. Now, some exceptions are made for high-altitude record flights and gliders, but those are really special cases. Now, as you can see, Class A airspace lies above the other controlled airspace that we've talked about in this lesson, so the airspace is not even shown on a sectional chart. Class A airspace begins at 18,000 feet MSL and extends up to and including flight level 600 or 60,000 feet MSL. Now you can think of Class A airspace as above because it's all high altitude airspace. Now it's also the only airspace not shown on the sectional chart. Now if your airplane climbs higher than 60,000 feet, you would actually re-enter Class E airspace. Now here are the pilot qualifications. First of all, the minimum pilot qualification to operate in Class A airspace is a private pilot certificate with an instrument rating. Now ATC separates all aircraft operating in Class A airspace. And here are the equipment and clearance requirements for an aircraft operating in Class A airspace. An aircraft must be equipped for IFR flight and must have two-way radios and an operating transponder with Mode C capability to fly in Class A airspace. And you must also have an IFR clearance to enter Class A airspace. Now let's review the various airspace categories that we discussed in this table shown here. First of all, we have Class A, B, C, D, E, and G airspace. Remember, Class F isn't used in the United States. Now, only IFR operations are permitted in Class A airspace, and both VFR and IFR operations are allowed in all other types of airspace. Now, only Class A and Class B airspace require a clearance to enter. You must establish communication with ATC to enter Class C and D airspace, and Class E has no ATC requirements when the weather is VFR. No contact with clearance is required when operating in Class G airspace. Now let's look at the pilot qualifications necessary for operating in the various types of airspace. In Class A airspace, you must have a private pilot certificate with an instrument rating. Only a student pilot certificate and sometimes an instructor's endorsement is required to fly in the other types of airspace that we discussed. Finally, two-way radio communications are required for Class A, B, C, and D airspace. Class E airspace requires communications with a clearance only when the weather does not meet basic VFR minimums. Now, in Class A and Class B airspace, ATC does separate all aircraft. In Class C, D, and E airspace, ATC separates IFR traffic and provides special VFR clearances. And no separation services is provided in Class G airspace. Now, ATC does provide traffic advisories in Class D airspace and Class E and G airspace on a workload permitting basis. Now, Class A airspace is not shown on sectional charts because it's above 18,000 feet, and you can see that here. However, Class B airspace is shown by solid blue lines, and Class C is marked by solid magenta lines. Class D airspace is indicated by segmented blue lines, and Class E airspace is marked by shaded magenta areas. And remember, Class G airspace isn't specifically marked on VFR charts.
Okay, let's take this time for another FAA test question. Here it is. In which type of airspace are VFR flights prohibited? Which of these three is correct? Let's review. You've seen this graphic before. Airspace summary, okay. Class A, IFR only. So if we go back to our question, in which type of airspace are VFR flights prohibited? The answer is C, Class A airspace. All operations are IFR, VFR is prohibited. Okay, moving on to a brand new topic. This time, special use airspace. Let's join Josh in the classroom.
Some types of airspace don't fall into the airspace classes that we've already discussed so far. They belong in a category of special use airspace because, as we'll see, they're designated for specific, unusual purposes, including military operations. We'll cover prohibited areas, restricted areas, warning areas, military operations areas, military training routes, and parachute jump areas. Now, one type of special use airspace is a prohibited area. Prohibited areas are established for security purposes, and they're just like they sound, prohibited. You can enter them only with special permission from the controlling agency, and as a civilian pilot, you are not likely to get the okay to fly in a prohibited area. Prohibited areas are indicated by blue lines and hash marks and are shown with a label like this one here. This is P56 and it overlies the White House in Washington, D.C. Now, restricted airspace is established over areas where it would be dangerous for civilian traffic to operate. And you see one right here. Restricted areas are often associated with military operations that include firing and dropping live weapons, test flights, and other hazardous activities. Now, they are marked with blue lines and hash marks and a restricted label that includes letters and numbers. Now, although it's generally best to avoid restricted areas at all times, you may be able to transition through a restricted area as long as it's not in use and you receive a clearance from ATC. Some restricted areas are active only part-time. You can find information about restricted areas on the Airspace tab on a sectional chart. That section lists the hours of operation and the controlling agency for each particular restricted area. Now, the controlling agency is usually the Air Route Traffic Control Center that covers that part of the country. Flight service stations also have information about restricted areas, and you can check with them as well. Now, a warning area is the next area we'll take a look at, and that marks airspace that lies over international waters and in which hazardous activities, like those associated with restricted areas, may be going on. Now, the FAA can't claim responsibility over airspace that they don't own, so you don't actually need permission to fly into warning areas, but as the name suggests, it is wise to keep out or at least check with flight service about what might be going on in a particular warning area. Next, a military operations area is commonly called a MOA. MOAs, like this one shown right here, outline areas where the military flies high-performance aircraft on training missions that may include aerobatics, formation flying, simulated air-to-air combat, high-speed, low-altitude tactics, maybe some air-to-air refueling, and other activities that create hazards to civilian traffic. Now, a MOA is marked with hashed magenta lines and is including a label and a number. The MOA is named Whitmore 1 MOA in this particular case and is shown by this circle right here. You do not need permission to enter a MOA as no live weapons are involved. but whenever possible, it's a good idea to avoid MOAs on your flight. If you do decide to fly through a MOA, you should verify its status before wandering inside. Now you can learn more about MOAs in the Airspace tab on a sectional chart. The information available there includes the floor and ceiling of the MOA, operating times, and the particular name of the controlling agency. Next, military training routes crisscross other types of airspace, and you can see a couple shown right here. They're most often used for high-speed military training flights below 10,000 feet MSL. Now, military training routes, or MTRs, are marked with shaded black lines, like we see a few right here, and they're often labeled VR for VFR flight or IR for IFR routes. Now, the 4-digit numbers mark MTRs that have no segments above 1,500 feet AGL. Routes that are labeled with a 3-digit number have segments above 1,500 feet AGL. Military aircraft using MTRs do not have to obey the 250 knot speed limit below 10,000 feet. So as you cross areas with military training routes, exercise extreme caution. Contact a flight service station to learn about activities on MTRs along your particular route of flight. Now, the last special area we'll discuss is the parachute jump area. The parachute symbol at Skydive Oregon, shown right over here, marks an area with busy skydiving operations. Areas with skydiving are listed in airport facility directories and on sectional charts. Pilots should definitively remain clear of these areas, as you won't often know the exact hours of their operation. The only way to positively identify when jumpers are in the air is to monitor the jump frequency. Many skydiving operators use the Common Traffic Advisory Frequency, or CTAF, at an airport to announce when the jumpers are in the air. Skydive Oregon, which is based at a private strip, does not even have a CTAF frequency, so you should stay well clear of that particular area.
Welcome back to the studio. This time, 2 FAA test questions. The first, which special use airspace may you enter without special permission from ATC under VFR conditions? A, B, or C? Again, a fairly straightforward answer. Which special use airspace? Military ops area. Answer C. Military ops allows you to enter without prior permission, even though you legally can. Not a real good idea to do so. All right? Let's take the second question now. Parachute jump areas are found in the following publications. Which of these, A, B, or C, is correct? Only one correct answer. Parachute jump areas. Okay. Found in which of these publications? The answer, C, once again, in sectional charts and in the airport facilities directory. Okay, we're going to move on to a brand new topic. This time, dead reckoning.
Now we're going to discuss pre-flight planning using a handy device, the E6B flight computer. Now the E6B is a circular slide rule designed specifically to help you make calculations for pre-flight planning. The E6B helps you solve all kinds of problems, including time, speed, fuel, and distance calculations. It can also help you solve problems associated with aircraft performance, such as calculating density altitude and converting temperatures from Celsius to Fahrenheit, and vice versa. The E6B flight computer and the plotter are your primary tools in planning a flight. Now, the E6B aids in computations needed for pre-flight planning. Now, these have been around for years, and they're also available in electronic format. When you use the E6B during flight to compute speed, wind, and estimate times, you are navigating by dead reckoning. Now, the FAA wants you to become familiar with this flight computer for a very simple reason. It doesn't need batteries, and it can be used anytime during a flight. So don't worry about memorizing all the directions for using this handy device. Guides for solving the most common problems are actually printed right on the E6B. Now, the E6B has two sides. The slide rule side has a rotating scale, and you use this to solve problems that involve time, speed, distance, and fuel. Now, you can also use the windows on this side to solve problems that involve altitude and temperature. Now, we'll discuss the other side used for calculating courses and solving wind problems a little bit later. Now you can solve most problems that involve time, speed, distance, and fuel by starting with the big marker called the rate arrow on this side of the E6B, and you can see that highlighted right here. The index, which is a big black arrow, marks speed, gallons per hour, distances, and other values depending on the type of problem that you want to solve. Now the numbers on the inner and outer rings that you see right here can represent any order of magnitude. For example, 6 could represent 6 or 60 or even 600. Now let's suppose you want to know how far you're going to travel during a specific amount of time. You have two pieces of information, your ground speed and the time. Using the E6B, here's how to work that computation. First of all, rotate the inner ring until the index is directly under the 12. Now in this case, the 12 represents our airspeed, which is 120 knots. Now suppose we fly for 1 hour and 10 minutes or 70 minutes. While holding the index on our speed, look along the inner scale to the point marked 70 or 1 hour and 10 minutes that you see right here. Directly above that mark, read 14 on the outer ring, and in this case, 14 equals 140 nautical miles. Now, let's say our airspeed remains the same at 120 knots. However, this time we only fly for 45 minutes. First of all, leave the index on the 12 for 120 knots and look along the inner ring to find 45 minutes. Now, leave the index on 12 for 120 knots, you found that, then read the distance directly above the outer ring. It's actually 90 nautical miles right here. Okay, now that we have the basics, let's go to our giant E6B and solve the following problems. Suppose we have time and distance, but don't know the airspeed. Let's say we've flown for 30 minutes and traveled 90 miles. What's our ground speed? Line up the time, 30 on the inner scale, beneath the distance, 90 on the outer scale. Let's take a look at that here. First we find 30 on the inner scale and we rotate that to line it up with 90 on the outer scale, just like that. Now, in order to find our ground speed, simply look along the edge of the E6B until we find our rate arrow right here. And in this case, the rate arrow is pointing at 18 or 18. So keeping all the units in the same order of magnitude, we know that this equals 180 knots. Let's take a look at another type of problem that we can solve using our E6B flight computer. In this case, it's a density altitude problem. I'll give you a scenario. Let's say we're at an airport and we want to determine what the density altitude is to determine if it's safe to take off. Well, we can determine our pressure altitude from the instrumentation we have in the aircraft, and we can also get the temperature from the local airport thermometer. Here's how we'd solve that problem. First of all, set the altimeter to 29 or 0.92 in your aircraft, and let's determine that it's 5,000 feet pressure altitude. We would then locate our pressure altitude on the scale of the E6B right here, where it says pressure altitude in thousands of feet. In this case, there's the 5, which indicates 5,000 feet. Now, we determined that the outside air temperature was 20 degrees Celsius, so we look at this scale right here, which has air temperature in Celsius. We look for the tick marks to identify 20 degrees Celsius, and we're going to rotate that until the 20 is just above the 5,000 feet, and you'll see it right there. Now, to determine our density altitude, simply look under this arrow right here labeled density altitude and read that our density altitude is just a shade under 7,000 feet.
Okay, next segment.
Okay? Airspeed correction. Okay? Let's take a look at yet another type of problem that can be solved using the E6B flight computer. In this case, it's an airspeed correction. And again, we're in luck because the instructions are printed right on the E6B. So, here's a situation. We're flying our aircraft at 10,000 feet and we want to determine what our true airspeed is. In order to do that, we need to determine what our pressure altitude is and what the outside air temperature is. I'll give you a couple of values. Let's say that our altitude, pressure altitude, is 10,000 feet and our outside air temperature is 20 degrees Celsius. let's look at the E6B to determine how we would solve that problem. First of all, locate our pressure altitude, again on this scale labeled pressure altitude, and we identified our pressure altitude as 10,000 feet, shown right here. Then we identified our outside air temperature, shown on this scale as 20 degrees Celsius. We simply rotate the slide until 20 degrees Celsius is opposite 10,000 feet, just like that. Now, if our calibrated airspeed is 120 knots, then our true airspeed is shown on the outer ring right here. And in this case, it's just a shade over 145 knots. Looks to be just about at 146 knots true airspeed. Let's take a look at another type of problem that can be solved using the E6B. In this case, it's a temperature conversion. Let's say that we're at an airport and we know that our temperature is given in Fahrenheit, and we'd like to determine what our temperature in Celsius is because all our performance charts in our aircraft are based on Celsius. Well, we're in luck because the E6B includes a temperature conversion scale at the bottom of the calculator. If we know that our outside air temperature in Fahrenheit, for example in this case, is 68 degrees, we simply look at the Fahrenheit scale to find 68. And in this case, it's right about here. Now, in order to determine our temperature in Celsius, simply look on the top side of the scale and read our temperature in Celsius, in this case, as 20 degrees Celsius. Now, the opposite side of the flight computer is used to figure wind drift and ground speed on your flight from point A to point B. Like the other side of the E6B flight computer, we're in luck because in this case, the directions are right at the top of the E6B. Now, we're going to work out an example problem with this side of the computer. You're going to be writing on the E6B flight computer throughout your entire career in aviation. You're going to keep this instrument around for a long, long time. So make sure you use a dry erasable marker or a number 2 pencil when you mark on the E6B flight computer. Here's the example for our problem. The true airspeed is going to be 170 knots. The wind will be 330 degrees at 39 knots, and true course is going to be 30 degrees. Here are the directions. Notice there are 6 steps involved on this side of the E6B used for ground reference. First, set the window direction under the true index. Then, mark the wind velocity up from center point. Third, set true course under true index. Then, slide the wind velocity up to the airspeed. Then your ground speed will read under the center, and your wind correction angle will read between the center line and the wind velocity mark. Let's perform these steps on the giant E6B. Step number 1, set the wind direction under the true index. Now here we can see the true index right here at the top of the E6B, and the wind direction is 330 degrees. So let's locate that along the top and let's set that right underneath the true index. Now, step number 2, mark the wind velocity up from the center point. Now, you may also want to make the grommet line up with one of these major velocity marks that you see right here. Here's our grommet in the center. In this case, we'll pick 150, and let's go ahead and line that up. There's the grommet, and there's 150. Now, the wind is at 30 knots, so 150 plus 30 is 180 knots. Let's take our marker and draw a line down to 150. Now, let's also put an arrow on this so we can remember which direction the wind is from. Step number 3, set the true course under the true index. Remember, here's our true index here, and our true course is 30 degrees or 030. So let's find that on our inner scale and set our true course right there. Now, step number 4, slide the wind velocity mark to the true airspeed. In this case, the true airspeed is 170 knots, so we'll move that wind velocity mark to 170. Here's our mark where we started, and there's 170. Now, step number 5, from that, we're able to read our ground speed under the center grommet. Here's the center grommet. So in this case, our ground speed is going to be 153 knots. Next, we'll accomplish step 6 to solve the wind correction angle. You can see here's the ground speed right here. And on this portion of the E6B, you'll see some wind correction angles. Notice here's 5 degrees and here's 10 degrees. So our wind correction angle can be read right here at the mark where we put our wind, right here at 9 degrees. And in this case, since it's to the left of our ground speed, it's 9 degrees to the left wind correction angle.
Do you think here's kind of a cute question, do you think there's any life left in the E6B?
I would like to think there is. At least I hope there is. The E6B computer allows a pilot to literally draw a wind triangle, and he gets to visualize the relationship between airspeed, wind speed and direction, and where he's going. I know that you can just punch in a few numbers on a calculator and get the same results even more accurately, but you don't have the sense of what the wind is doing to the airplane. You don't think in terms of crab angles and drift angles as you do when using an E6B. I think the E6B is essential for learning the relationship between wind, track, and the airplane, what it's doing. I used to teach, and I still like to teach new students to actually draw wind triangles right on the chart and get a sense of what's happening, the relationship between wind and the aircraft. And the E6B helps to do that. But the calculator, it's so easy to stroke a wrong key and come up with the wrong information. And if you don't have a good sense of what to expect as an answer, you might rely on the wrong one.
Now, we're done using the E6B flight computer for this problem, but there are still more steps to find the answer. We still have to come up with a compass heading. We still also have to compute our variation and deviation. And the final answer takes 4 steps. And the good news is that we've already figured out a couple of our 4 steps by using our E6B. We've already computed our true course and our true heading. Finally, we'll compute the magnetic heading and the compass heading. Now, using the plotter that you see right here, we're going to draw the course line from point A to point B with the center point of that plotter at some point along our course line. There's the center point right there. Then we would rotate the compass of the plotter to align it with a line of longitude. Then you center the compass rose. Now, these lines of longitude appear about every 30 minutes on the sectional chart. Now, you have to also account for wind direction and how it is going to affect your ground track. Now, here's an example. Here is an airplane on a ground track of 360 degrees, but notice that the wind here is from the east. Now, to maintain this track of 360 degrees, you have to take a bite out of that wind. In this case, about a 20-degree heading to maintain a ground track of 360 degrees or to the north. Now, this emphasizes how you have to adjust your wind on your compass heading. Here's how we get to the compass heading. True course plus or minus our correction angle gives us our true heading. Now, before we continue, you have to understand a new concept, and that is the difference between a magnetic North Pole and a geographic North Pole. The difference is in location between these two areas, and the magnetic and geographic areas cause variation. And that variation is plotted on our aircraft sectional charts and our WAC charts as something called an isogonic line. Now, isogonic lines are shown on sectional charts. This happens to be one right here as a dashed magenta line. This one happens to indicate 5 degrees west, and you can see that right here. Now, there's a rule of thumb to remember with isogonic lines. East is least, west is best. Now, when you have an eastern isogonic line, say 5 degrees east, you subtract from your true heading. When you have a western isogonic line, you say west is best. So 5 degrees west, you would add that to your true heading. Now, next up is the compass or magnetic deviation. Within an airplane, you have all sorts of things that cause problems, such as an engine and magnetos and electrical instruments and magnetized metal parts that will affect your compass. Because of these magnetic influences, the compass needle can deflect from its normal reading. This deflection is known as deviation. Now, a pilot or mechanic should determine how much deviation occurs with the headings of the airplane because of this magnetic field. This technique is called swinging the compass. Now there should be a compass card in the cockpit of the airplane you are flying, and this gives you the corrections you need to use for north, south, east, and westerly headings. Remember that deviation varies from airplane to airplane because each airplane is going to have its own magnetic field depending on how many instruments are in and out of the aircraft at one particular time. Now let's review the plotter. The plotter has two sides. One side is scaled in nautical miles. The other side is scaled in statute miles. For this example, we'll use nautical miles. Notice that there are two separate scales. The outer scale is for sectional charts and the inner scale is for WAC charts, or what are called World Aeronautical Charts. Don't begin your measurements out here at the end of the plotter. Start them along this 0-point reference line. This little arrow is going to indicate your true course line.
Welcome back. Let's take time for another FAA test question. Determine the compass heading for a flight from Claxton Evans County Airport, Area B, to Hampton-Varnville Airport, Area C. Which of these three is correct? Let's give you what the FAA will give you for this question. The wind is from 290 degrees at 18 knots. The true airspeed is 85 knots. And of course, areas B and C are shown in your FAA test supplement booklet. Let's join Josh back in the classroom as he solves this problem for us.
Now let's begin to work the problem together. Using the plotter, draw that course line. Here is Claxton Evans County Airport right down here, and here is Hampton-Varnville Airport, and you see that right up here. And there is the course right there. So the total distance is 57 nautical miles, and we read that off the scale on our plotter. Next, we'll plot the course. Center the plotter and mark the true course. Now this portion of our plotter rotates right here. So you'll line it up at 0, and this gives you the true course of 45 degrees, and you can see that right there. Now let's use our E6B computer. Remember, from our previous example, place the wind of 290 degrees under the true index. Then move the scale and place the grommet over the major division. Now place the major division under the grommet. Then you will count up from the grommet to the wind mark. In this case, you can see that right there. And it's going to be 18 knots. Now here's the grommet from the major division up 18 knots, then mark it. Then draw the arrow down towards the grommet, and you'll see that right here. Now rotate the compass card to continue to the true course of 45 degrees. Then move the scale down to the true airspeed of 185 knots. Here's the ground speed up. Notice there's a tailwind. In this case, it's a 12-degree left wind correction angle. It's time to commute the magnetic variation. Here are the isogonic lines, and in this instance, it indicates a 5-degree west isogonic line. Remember, west is best, east is least. In this case, with a west heading on west isogonic lines, we'd add that to our true heading. So in this case, we add 5 degrees. Finally, to get our compass heading, we're going to use this formula that's found at the top of the E6B. We had our course. We determined our true course was 45 degrees. Then we have to account for our left wind correction angle. In this case, it was minus 12 degrees. So 45 minus 12 gives us a true heading of 33 degrees. That's important. Then we add our west variation, and we know we add it. In this case, it was plus 5 that we found on the isogonic line, and we add it because, remember, west is best. So 33 plus 5 gives us a magnetic heading of 38 degrees. We're almost done, but not quite. We have to add our compass deviation. In this case, it's minus 3 degrees. Now, the compass deviation will always be given to you in the figure or the problem because it does vary from aircraft to aircraft. So 38 degrees magnetic heading minus the compass deviation equals a compass heading of 35 degrees.
Our thanks to Josh for solving that problem for us. A lot of hard work went into that. Now let's take a look at the question again to give you the answer. Determine the compass heading for a flight from Claxton Evans, Area B, to Hampton-Varnville, Area C. Of course, the final product of all the calculations, 035 degrees is the compass heading. Okay, we're going to have a new topic coming up right now. This one, turbulence. Now, how does turbulence avoidance factor into flight planning, the flight planning process?
Big time.
Really?
Big time. people like to think that, oh, he's an experienced pilot, he doesn't mind turbulence. I don't like turbulence. I don't like it any more than the newcomer to flying. I think turbulence is uncomfortable. It's a pain in the you-know-what, literally and figuratively. I like a nice, smooth flight. So it figures prominently into my flight planning. And I always try to anticipate the kind of turbulence I'm going to get on a given trip. Whether it's generated by the wind, we call that orographic turbulence, or whether it's going to be generated from below, convective turbulence, and try to plan a route as best I can to avoid that kind of turbulence if possible, or to minimize it. I don't like turbulence, and the passengers that I like to take with me don't like turbulence either. I don't know anyone who enjoys it, and it's a misconception to think that because someone's experienced, they don't mind it. Well, let me tell you, they do. I don't like it.
Now let's talk about a flight in turbulence. First of all, you don't plan to fly in turbulence, and in fact, during your pre-flight preparations, you use weather briefings to help you select a route that avoids a bumpy flight. But if you encounter turbulence, you need to know what to do. First, establish a level attitude. Try to keep the airplane upright, but don't fight to maintain altitude. That could impose undue stress on the aircraft. Now, you should slow the aircraft down to maneuvering speed or slower to help prevent additional stress on the aircraft.
Now, do you actually prepare for having a power failure in flight?
Absolutely.
Do you?
Absolutely. It's more than preparation, it's anticipation. In flying a single engine airplane, I always anticipate, always believe that that engine's going to quit. You know, when you think about it, you take a piston engine, and it's got all of these moving parts inside. They're thrashing around. There's high pressure explosions and compression taking place, and all these little things are going crazy in there as compared to a jet, which is very simple by comparison, that you almost have to say to yourself, these engines really can't take that kind of abuse. Well, we know they can. They're very, very reliable. But I like to think that, well, once in a while it's going to fail me. And I've had 3 engine failures in piston-powered airplanes. And fortunately, I was able to land safely in each of those 3 cases. I like to fly where I know I can make a safe landing in the event of an engine failure. It's something that we learn as student pilots and we tend to forget about as we become more experienced. But believe me, it pays handsome dividends to anticipate an engine failure and always fly where you have the greatest chances of being able to put the airplane down. For example, going from LA to Vegas. You can go direct through Cajon Pass to Las Vegas. You fly over a lot of desert. But you know, if you fly about 10 or 15 miles off to the right, you're flying over a major highway, which most of the time is empty. I mean, isn't that a great place to land an airplane? But not only that, not only is it nice to have a place to put down in the event of an engine failure, but you know someone's going to find you right away. I mean, the highway does have traffic on it. Rather, if you land out in the desert somewhere, people might not find you. It's something that really bothers me that a lot of pilots do. They'll taxi out and they'll go through their checklist, their before takeoff checklist. And one of the items, of course, is to always be on the fullest fuel tank for takeoff. And I watch people just before takeoff switching to the fullest tank. And you know, that's not a good time to do it because you don't know the integrity of the fuel flow from that tank to the engine. And if you take off right away, you haven't had a chance to verify that you do have fuel flow from that tank to the engine. So what I always tell people to do, and I strongly recommend that they do it, is when they first get into the airplane, before they start the engine, is to think, which tank do I want to use for takeoff? Switch to that tank before starting the engine. And then you can start the engine, taxi out using fuel from the selected tank, verify the integrity of the fuel system, verify that the fuel is good, it's not water, make your run up, and by that time you know everything is operating normally. Take off on that tank with some assurance. Don't wait until just before takeoff to switch to the fullest tank.
Outstanding. Barry, we appreciate your insights very much. Thanks for being with us in the studio
My pleasure.
today.
They tell me if you wind me up, I can keep on going.
There you go. Well, we'd love to have you back, and if we can work that out, we'll do it.
Anytime.
All right, let's go back to our instructors at this point.
If you experience a power failure in flight, try to remain calm while acting quickly to assess your situation. If you're at a typical cruising altitude, you do have time to troubleshoot the problem. Your first responsibility, as always, is to fly the airplane. In this case, that means immediately establishing best glide speed to give you time to locate a suitable emergency landing site, run the appropriate emergency checklist, and if possible, to contact ATC for assistance. Then second, locate a suitable landing site. If you can't get that engine restarted, you're going to have to land somewhere, so you need to find a suitable landing site right away and start maneuvering towards it. Next, troubleshoot the problem using the available emergency checklists. You want to try and restart that engine, and using a checklist will help you to do things in an organized fashion. Finally, you want to communicate. Let somebody know that you've just lost your engine and that you are in trouble. If you can, tune the emergency frequency to 121.5, use the last frequency you were transmitting on, or perhaps a nearby Unicom frequency to let anyone know that you're having trouble and where you are. Handling an in-flight power failure means you follow this priority list: aviate, navigate, and communicate. Well, that finishes this lesson. I'm Josh Pruzik, and it has been my pleasure to be your instructor for this lesson on en route flight.
Okay, now for our final FAA test question for this lesson. The question: in the event of a power failure, immediately after takeoff, you should do which of these, A, B, or C? Okay, in the event of a power failure, immediately after takeoff, you should B, fly the airplane first, locate a suitable landing site, troubleshoot with your checklist, and communicate. We know that en route power failures happen very rarely, and if it does occur, you should always use the proper procedures. Okay, that wraps up our lesson number 9. When you're ready, please tackle lesson 10, navigation.